First question, does negative 3 satisfy 3x plus 3 equals negative 4y? Now the ordered pair of 3, negative 3 indicates an x value and a y value, and that's implicit. So 3, negative 3 is a point x, y. So x equals 3, y equals negative 3. Now, does x equal 3, y equals negative 3 satisfy this equation? To find out, plug in. We plug in 3 for x, so 3x becomes 3 times 3. 3 remains what it is. And that should equal negative 4 times y, where y equals negative 3. Well, we do the arithmetic. We get 9 plus 3 equals 12. And it does appear that we end up with 12 equals 12. So this point appears to satisfy this equation. Now, just a little aside, this equation represents a straight line. You can solve for y, determine the slope and the y-intercept. You're going to find that the slope is negative 3/4 and the y-intercept, which occurs when x equals 0, is also at negative 3/4. So if I said that right, the graph is going to look something like this. And the point 3, negative 3, if I come over 1, 2, 3 units, I'll go down 1, 2, 3 units, and I'll be on that graph. So the point 3, negative 3 would lie on the graph of this equation. Now that's not part of the goal of number 1, it's just to know that if we plug these coordinates into this equation, we can test to see whether we get an identity or not. In this case, it appears that we do. Next, we want to find the domain and range, and I smudged out the M here, and still got a smudge, we'll have to live with that. Domain and range of this relation. So this is a relation, might be a function, might not be. In this case, it wouldn't be a function because you got 3 here and 3 here, but we'll get to that later. Right now we just want to know what the domain is and what the range is. Well, the domain consists of all the first coordinates. So the domain is what? First coordinates are 2, 4, negative 4, 3, and 3. If I want to list that, and of course I list the domain as the set of those values, I'll start with the least and go to the greatest. The least is negative 4, and then next to that, the next least number is 2, and then we've got 3, and we've got 4, and this is the domain. Notice I didn't list 3 twice, we're listing sets. Okay, it doesn't matter how many times I list an element of a set, either it's in the set or it isn't. And it doesn't matter if it would be in there multiple times. If it's in there, it's in there. So we don't need to list 3 twice. We only list it once. So here's our domain. Our range is what? It's the set of second coordinates. That would be 3, negative 2, 4, negative 2, and negative 4. So again, going from the least to the greatest, negative 4 is the least, then I believe negative 2, and I would normally ask a class to let me know if I missed something, because I could. And then we have 3, and then we have 4. Okay, now, again, did I miss something? Yeah, okay, no. Okay, negative 2 appears twice, but we don't list it twice in the range. It's either in the range or it isn't, and in this case, it is. So here's our domain, here's our range. Okay, now the third task, we want to identify the domain and range from a graph. Okay, now for the part of the graph that we see here, and let's just confine our attention to the part that we see, it appears that every point from about every x value from here over to here has at least one associated y value. Okay, so every x from here to here, whatever x it is, if we pick this x, well, we've got two y values. We've got one up here and one down here. We have a y value here and a y value here. Okay, the domain is therefore, let's just say this is -11 and this is 11. That looks about right. And when we have a graph like this, we just make an estimate. The domain would be maybe the interval from -11 to 11. Whether that's an open or closed interval, when you have a graph like this, unless you have a big closed dot on these endpoints, you're going to assume maybe that it's an open interval. And we don't have a big dot on these endpoints. The range consists of what? Well, it consists of all possible y values. So we've got y values that go as high as this and as low as this. So all the y values, and let me change my coloring a little bit here. I'll go with purple on the range. I went with different colors over here, but that doesn't matter. Okay, so the range would be this interval, and down here we have a similar interval. Okay, all the y values between here and here are taken at some point on the graph of the function. So if we want the y value here, well, actually there are two places where we get that y value. If we want a y value here, there are two places where we get this y value. And there's maybe only one place where we get the y value at the peak of this shape. And only maybe one y value where we get this. In any case, the range appears to go from about, what is this? There's -5, there's -10. Maybe that's -8. And maybe that's, if 5 is here and 0 is here, that looks like -3 or -4. I would say maybe the range is from -8 to -3.5. But we do the union of that with the interval from here to here. Now that looks like about 3, and that looks like about 8.5. So that would be 3, 8.5. Now I've written both of these as open intervals. Is that appropriate? Well, at the bottom here where we have the -8 value, that'd be about -8. Okay. The open interval might be appropriate because we're not sure whether we include the endpoints here. It looks like if this is maximum value is 3.5, it looks like maybe that value is actually taken by the function at this point. So we probably want to say it's a closed interval here. Okay, so the value that we get here, if it's -3.5, would actually be included, so we'd make this a closed interval. Okay, and over here, we'd probably do the same thing here. If we think that 3 is the value at this point, then we make this a closed interval. So, and I should have done that in the first place, but I was busy talking. Okay, so we would write it like so. Okay, on the fourth one, we want to know if this relation here is a function. Okay, well, the only thing necessary for a relation to be a function is that you have just one answer to what's the value of y that goes with this value of x. Now, to give you an example of something that isn't a function, because it turns out that this one is, let's go back to this relation. This relation is not a function because if I say, okay, x is 3, what's y? what are you going to say? Well, y is negative 2 because x is 3 here, so y is negative 2. But I could say, wait, x is 3 and y is negative 4. So I think y is equal to negative 4. You can think y is equal to negative 2 when x equals 3. I think it's equal to negative 4 when x equals 3. If it's possible to disagree, then it isn't a function. If there are two different y values for the same x value, it's not a function. If there's exactly one y value for every x value, then it is a function. So what do we have here? Our x values, well, let's just try to make a table. Let's do a table of y versus x. Okay, the least value of x is negative 6. And at that value, y is negative 5. Okay, and there's no other negative 6. So we know that when x is negative 6, y is negative 5. There can be no disagreement. There's only one y value that goes with x equal negative 6. If the next least y value is negative 3, it gives us x equals negative 2. Well, that's fine. We don't have any other negative 3's so far, at least. So there's no ambiguity about the value of y when x equals negative 3. Next value would be 2 and the y value is 4. Not a problem. Okay, the next value of x would be 4 and the y value would be 2. And we have value of x equal to 7 and the y value is negative 5. Okay, well, there's no problem with any of that, is there? Okay, the x values are negative 6, negative 3, 2, 4, and 7. And negative 6 occurs just here, so that y value is good. Negative 3 occurs just here. Y is equal to negative 2, so we can definitely say that if x equals negative 3, y equals negative 2. If x equals 2, y is definitely 4. There is no other value of y that's associated with 2. If x is 4, y is 2. And that's the only value of y that we get for x equals 4. And similarly, if x is 7, y is equal to negative 5. And there's no other value of y. Now, you might say, well, we got negative 5 here and we've got negative 5 here. That's the same y value. Well, that's okay. As long as we can answer the question, for this x, what is y? As long as every x has just one y with it, it's a function. So, yes, for every x, we can say what y is. Okay, now the last question, and I'm kind of looking at the camera because we're running short on time here, but the last question, I think we can get through this, is on its domain, is this a function? Now I just sketched these vertical lines in here, which appear to be the lines for x equals negative 1 and x equals 1. The domain of this function is all possible x values, so here's your domain. And we could list that as an interval, but you're not asked to list the domain, so I'll just indicate that here's your domain, and probably it includes negative 1 and 1. Now, for any given x value, what's the y value? Let's just take an x here. Well, you see that we have several answers. Y could be this. Y could take this value here. 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 You could estimate the value of y at every one of these points. So there are many answers. There are many y values for any x in the domain. Okay? Any x from here to here gives you more than one y value. I've got an eye on the camera, going to have to cut off now.